Imagine dropping a point onto a mathematical plane and feeding it through a repeating process. Usually, the point bounces around chaotically, but occasionally that process forces the point into a tighter and tighter path, eventually spiraling into one exact, inescapable destination. When an input passes through a function and comes out completely unchanged, when f of x simply equals x, mathematicians call that a fixed point. Finding a root where an equation equals 0 can be difficult, but rewriting that problem into a search for a fixed point changes the nature of the search. We stop hunting for a static coordinate and instead let the function drive the points directly toward the solution. To guarantee that this dynamic process actually works, we need a specific environment. First, we need a metric space. Simply put, this is a mathematical setting equipped with a rigorous, consistent rule for measuring the distance between any two points. Look at this text from Rudin's Principles of Mathematical Analysis. The second requirement is that our metric space must be complete. In plain terms, a complete space has no microscopic gaps or missing limits. If a sequence of points is clustering together infinitely tightly, the location they are aiming for actually exists inside that space. The final requirement is the function itself. It must be a contraction mapping. This formal inequality tells us that if we take any 2 points and plug them into our function, the distance between their new outputs will be strictly less than the distance between the original inputs, scaled down by a constant factor c. There is a critical constraint here. That constant c must be strictly less than 1. And crucially, this exact same ratio must apply globally to every single pair of points in the entire space. When you pair these concepts together, a space with no holes and a function that universally compresses distance, you construct an environment where infinite aeration becomes trapped. The points have nowhere to go but together. This brings us to the Banach Fixed Point Theorem, also known as the Contraction Principle. It states that if x is a complete metric space, and phi is a contraction on x, then phi has exactly one fixed point. To prove this theorem, we have to satisfy 2 separate mathematical burdens. First is existence. We have to definitively prove that at least one fixed point is actually out there waiting to be found. Second is uniqueness. We have to prove that it is mathematically impossible for a second, hidden fixed point to exist anywhere else in the space. This theorem is constructive. Its proof provides the specific iterative algorithm needed to physically find the answer. We start at x0. Iterating yields x1, with distance d. Feeding x1 back gives x2. By contraction, this new distance is bounded by c times d. Projecting forward, by the nth step, the distance shrinks exponentially to c to the nth power times d. To prove this sequence is truly clustering together globally, we need to measure the distance between our current position, step n, and any random future point arbitrarily far down the line, step n plus p. To do that, we use the triangle inequality. By expanding this distance, we break a massive leap into a long sum of consecutive individual step distances. And since we know each of those consecutive steps shrinks exponentially, we can bound this entire expanding sum using the formula for an infinite geometric series. Because our constant c is strictly less than 1, as n grows toward infinity, the value of that geometric series bound crashes to 0. Since the maximum possible distance between any future points shrinks to 0, the points are universally clustering. We have successfully proven that our sequence is mathematically Cauchy. Generating a Cauchy sequence is only half the battle. The points are clustering, but we must ask, what exactly are they clustering around? This is where we invoke the completeness axiom established earlier in Chapter 3. Completeness acts as a safety net. It guarantees our Cauchy sequence doesn't fall through the cracks of the space. Because the space is complete, the sequence absolutely must converge to a real point, let's call it P, that exists inside the space X. Furthermore, because contraction mappings are continuous functions, we can pass our limit through the function. This proves that the output of P exactly equals P. The algebra drove the sequence together, and the topology of completeness ensured it hit a target. Existence is proven. Now we shift to our second burden, uniqueness. To prove this, we assume the opposite, that 2 distinct fixed points, P and Q, both exist in our space. If we apply the contraction definition to these two hypothetical points, we look at the distance between them. Because they are both fixed points, mapping them doesn't move them. The distance between their outputs is identical to the distance between their inputs. But our contraction rule states the output distance must be less than or equal to c times the input distance. Since c is strictly less than 1, a positive distance cannot be strictly less than itself. The only way to resolve this is if the distance is exactly 0. Point P must be point Q. Only one fixed point is possible. So what happens if we attempt to use this theorem but ignore the completeness requirement? Consider a counterexample. The function f of x equals x divided by 2, defined on the open interval between 0 and 1. This valid contraction shrinks the distance by half each iteration. The sequence clusters tightly as it approaches 0, proving it is Cauchy. But here is the failure. The sequence chases the number 0. Because our interval is an open set that does not include its boundaries, the number 0 does not exist inside this specific mathematical space. The iterative process fell through the floor. This proves that the hypotheses of Banach's theorem, specifically the completeness of the space, are load-bearing pillars of the analysis. The contraction principle serves as the theoretical bedrock for how computers and physicists solve real-world problems. In the field of numerical methods, it provides the underlying guarantee of absolute convergence in complex root-finding algorithms, much like Newton's method. It plays a crucial role in differential equations, powering Picard iteration to prove that unique solutions exist for complex initial value problems. And finally, its underlying mathematical philosophy operates in modern optimization, giving extreme rigor to advanced computational techniques like gradient descent. Wherever continuous mathematics relies on iterative refinement to calculate an answer, the Banach Fixed Point Theorem is usually the silent engine guaranteeing that the process won't stall. Let's review the core mechanics we've established. The formula is non-negotiable. Take a contraction mapping, apply it within a complete metric space, and you are guaranteed exactly one unique fixed point. Furthermore, simple iteration will find it. The contraction principle effectively demonstrates how a simple, universal distance-shrinking condition simultaneously forces existence, uniqueness, and convergence all at once, making it one of the most elegant results in modern mathematical analysis. If you found this breakdown helpful, leave a comment below with which theorem from Rudin's Principles of Mathematical Analysis you'd like us to deconstruct next. And don't forget to subscribe for more deep dives into advanced mathematics.